This is lessons 9 and 10 on scientific notations and the operations we can do with scientific notations like addition, subtraction, multiplication, and division, and I'll be showing you examples of all of those. But we need to start with the basics of scientific notation. So first I'm going to show you how to just manipulate numbers by multiplying them by powers of 10. So I want to change all of these numbers into 234.567. So on this first one, we have a decimal right after the 2. But I don't want the decimal to be right after the 2. I want my first number to show 234.567. So I need to be thinking, I need to move this twice. I need to make this number appear 2 decimal places bigger than it actually is. In math, you can do that. Problem is you always need to keep things balanced. So if I'm making something bigger by 2 decimal places, I have to essentially make something else smaller by 2 decimal places. And the way that works is we know that when you multiply something by 10, you're actually moving it up a decimal place, like 3 times 10 equals 30. That 3's moved up a decimal place. So here I've made something bigger by 2 decimal places, so I need to make this smaller by 2 decimal places. So this is going to be a -2. So I can rewrite this number to be 234.567 times 10 to a -2. And this actually equals the original number that was there. Let's try the next one. We have 234.567. Oh, well here, that's actually the number we want. So we don't need to move that decimal at all. That decimal's happy right there. So what kind of power of 10 can I multiply by that it won't move? You're thinking 10 to 1 moves it one place, 10 to a -1 moves it one place. 10 to the 0, though, won't move it at all because 10 to the 0 is just 1. And you can multiply any number by 1 and it doesn't change it. So we can actually just keep this and just put it times 10 to a 0 because it's not going to change it at all. Let's take a look at this next one. I have the decimal right in front of the 2, but I want it right after the 4. So I need to make this number bigger by 3 decimal places. So I need to make something else smaller by 3 decimal places. So to rewrite this number, so I have 234 as that first number, is this exact same number that we started with. Here we have a nice whole number, and all whole numbers actually have a decimal at the very end. We don't typically write it just because it's in bad form. You don't need to put it there. We all recognize that it's there. But there is one right at the end, and we need to be thinking, I want to move it 3 spots forward, 3 spots to the left, which means I'm actually making this number smaller by 3 decimal places. And if I'm making something 3 decimal places smaller, I need to make the 10 bigger, so it's going to be a +3. So if I rewrite this one, because this essentially means that this number actually isn't this small, it's actually 3 decimal places bigger. That's all that we're representing. The powers of 10 are showing that this isn't actually what the number means. It's actually 3 times bigger, 2 decimal places smaller, 3 decimal places smaller. So let's get down a definition for scientific notation. Scientific notation is just a way for scientists and mathematicians to use really, really small or big numbers without it being a pain. So there's always a standard form that it's in. And it's actually always 1 digit to the left of the decimal times a power of 10. So realistically, if we wanted a scientific notation, we should have 1 digit to the left of the decimal times some power of 10. So some power there would be our scientific notation. So now let's practice turning some numbers into scientific notation now that we know what that is. So on our sheet, we have this first number. We have a decimal, 2 zeros, and then a 364. Now remember, scientific notation says that we need one number past the decimal, and that number can't be 0. So what we're going to do is we're going to take this first number, this 3, and that'll be our first number to the left of the decimal. Now, we still need to attach that 6 and that 7. That's 4. So let's attach the 6 and the 4. So we're going to change this number into 3.64. Then you're thinking, okay, next part of scientific notation is times some power of 10. And you're right. Now, thinking back to the activity we just did, we have to keep these balanced. So I need to be thinking that the decimal was here, but I actually moved it 3 spots to be right behind the 3. And I made this number bigger by 3 spots. Well, if I made this number bigger by 3, I need to make the 10 smaller by 3. So I'm going to put a -3 there. And that's how you change things to scientific notation. So this number in scientific notation represents this original number. It's saying 3.64, yeah, those are the numbers involved, the actual digits. but where that decimal is actually 3 digits away. It's actually 3 digits smaller. Let's go down below. You can see that, yes, this would be a number that's not very nice to work with. For most of you, probably wouldn't even fit into your calculator. So let's change it to scientific notation. I need one number out front, so that's going to be our first digit, that 8, because it can't be a 0 out front. We need to tag along everything else. So 8's our number to the left of the decimal, and then you just tag on everything else in order. Then we need it times 10 to some power, and then we can find out what power that is. I need to move this decimal to be here, so it represents exactly what's here. So let's see how many times we move it. 8, 9, 10. I made this number bigger by 10 decimal places, so I need to make this smaller by 10. So I'm going to put in -10. So hopefully you're recognizing that the negative numbers are showing that this number is actually a lot smaller than it appears. Same thing here. I have a negative, and so the bigger the negative is, the more smaller this actually is. That's probably bad grammar. The smaller this number actually is. So now let's take a look at some bigger numbers. 130,000. So we need some number before the decimal. So we'll just take our first actual number, because it can't be a 0. So we'll take our 1, put a decimal, and then carry out everything else. Normally we don't tack on the zeros, because on decimals, technically there's an infinite amount of zeros after them, and it's really bad form to write those. So we're just going to leave this as 1.3. If you tack on the zeros on your test, I won't mark it down. It's just not good form. So we have 1.3, one number to the left of the decimal. We need times some power of 10. So let's find out how much we need to move this decimal. So this is a whole number, so all whole numbers have that decimal right at the end, and we need to move it to be right next to the 1. So let's see how much we move it. 4, 5. I moved it 5, and I made this smaller by 5 decimal places. So I need to make this bigger by 5. So remember that 10 to the 5th power is saying this 1.3 isn't so small. It's not actually 1.3. It's actually a lot bigger than it appears. Let's take a look at this next one. This one's not so happy looking because it doesn't have as many zeros, but it'll still work out. So we need to take our first actual number, that 1, keep it to the left of the decimal, then everything else can be carried behind. Now we need it times 10 to some power, so let's see what that power is. This is a whole number, which means there's a decimal right at the end that we don't actually see, but we can write it in for now. And we need to move it to here, so let's see how many times we move it. 6 places. We're making this number 6 places smaller. So I need to make this 6 bigger, so it's going to be a +6. So hopefully you notice now that when I am dealing with big numbers, you're going to have a positive exponent because we're actually saying these numbers are bigger than they appear. So let's write down our rules, all these words that are underneath. If you are making the number bigger, like here, we made the number bigger, you need to make the exponent smaller or negative. So if we're making the number bigger, just like here, we made the number bigger, we're going to need to make the exponent smaller, or you can think of it as making it negative. Next thing, if you are making the number smaller, like we were there, because it's not 130,000, we changed it to 1.3, so we made it smaller, you need to make the exponent bigger to counteract it, or positive. We can also think about it in a different way. Negative exponents represent small numbers, just like here. This negative exponent actually represents that this number is much smaller than it appears. Same thing here. This number is actually much smaller than it appears. Whereas positive exponents represent big numbers. Just like over here, this 1.3 is not just 1.3, because this +5 exponent says that this 1.3 is actually much bigger than it appears. Same thing down here. This 10 to the 6th power says that, hey, this number's actually bigger than this little decimal that's right here. All right, now let's take a look at going the other way. Being given scientific notation and expanding it back out to its true number. So we have 1.837 times 10 to a -4. So we have to remember that -4 means that this number is actually smaller than it appears. It's actually 4 decimal places smaller. So sometimes this will help you, is to add just extra zeros. So first, let's decide which way we're moving the decimal. So you should be thinking, well, I'm going smaller. So if I go this way, the number's getting bigger. So I need to go to the left. I need to move this decimal places 4 places to the left. So let's add some zeros on this tail end. So I need to be thinking that I'm going to move it from here over 4 times. 1, 2, 3, 4 to right there. So we need to move that decimal place 4 times over to the left to make this number the original small number that it was. So let's rewrite this. We always have a 0 in front because otherwise it's actually improper to write. We have 3 zeros, then our 1, 8, 3, 7. Now, how do we know that we're right? How do we know that this was actually the way that this ended up? Well, we can just count it out again. If we moved it into scientific notation again, moving this decimal to be right here, we would have made it bigger by 4 decimal places, so we would have had to have a small 4 here, a negative 4 here. So yeah, it's correct. Let's try this next one. We have a 9.83 times 10 to a 0. Well, that 10 to the 0 says that it moved nowhere. It didn't move at all. 10 to the 0 is 1. So this number actually is still 9.83. That is the original number. Just they put it into scientific notation that way. We have a 2.8 times 10 to a 5. That 10 to a 5 says that this number is actually bigger by 5 decimal places. 2.8, and then add on some extra decimals because we need to make this number bigger going this way. So we need to shift everything that way. So we need to make it bigger 5 decimal places. So let's move it 5 decimal places. 1, 2, 3, 4, 5. So it's going to stop right there. So let's write what that number is. 28 and then 4 zeros. So it's actually 280,000. How can we check that we're correct? Well, let's change that back to scientific notation. If I wanted to change this to scientific notation, I start right at the end because that's where my decimal is, and then move it to right behind the 2. That's 1, 2, 3, 4, 5 spots, making it smaller, so I need a positive 5 as my power. Now looking at the very last one, we have, a pretty nasty decimal, but that doesn't really matter. What matters is this power. This power says that it's bigger by 2 decimal places. So let's make it bigger by 2 decimal places. If I'm making it bigger, I need to move this way. Okay? I don't want to make a bigger decimal. That'll actually making it smaller. So I want to make it bigger going this way. So the decimal's here, and I move it 1, 2. So that just becomes 629 point, then the rest of that jump. So how do we check that we're correct? Well, just go backwards again. Decimal's here. Scientific notation needs to move it here. So I move it 2, making it smaller by 2, which means that the exponent needs to be bigger, a positive 2. Okay, now let's look at an example when we need to subtract scientific notation. So take a look at the problem. Find the difference in the populations of Texas and North Dakota. So already off the bat, you're saying, okay, what am I doing with these? Even if I hadn't told you that we're subtracting, this word here, difference, tells you that we're subtracting because difference is the end result of subtraction. So if you really even need to, if you want to, you could just write in subtraction. So finding the difference, so we're going to have to do subtraction. Finding the difference of the populations of Texas and North Dakota. Texas has about 26 million people, and North Dakota has 6.9 times 10 to a 4. So here we're given the information in 2 different ways. So I'm going to show you the answer in 2 different ways. So let's do it the long way, as if we didn't know scientific notation. So Texas has 26 million, so let's write out that number. North Dakota has 6 times 9 to a power of 10. Now we just learned how to expand that out, so we need to do that. It's a 6 and a 9, and then we need to make it bigger by 4 spots. So it was here, so there's 1, 2, 3, 4. Let's check that we did it right. It was here, and it goes 1, 2, 3, 4 to make it bigger by 4 decimals. So wow, that's a really big difference between Texas and North Dakota. So what's the difference between Texas and North Dakota? Well, we would just need to plug it into our calculator. Hopefully our calculator does this. So we need to subtract 26 million. We need to subtract, the 69,000 from the 26 million. Now you can go through and do it the long way, the whole borrowing. I'm going to cheat and use my calculator. So the difference is 25,931,000, approximately. Now, if I didn't have my calculator with me, that would have been some really ugly, long subtraction. So that's why I'm going to show you the scientific notation way, because it works even without having your calculator around. So obviously if this is the scientific notation way, I probably need both numbers in scientific notation. So let's change Texas. Texas is 26 million. Now the decimal is right here. I need to move it to here because I need to be 2.6 times 10 to some power. So let's count up what that power is going to be. 7, because I need to represent the fact that this number is actually 7 decimal places bigger in reality. And I don't need to change North Dakota because they were nice enough to give it to us like that. We can't just subtract these the way they are right now. There's actually something we need to do first. We need to change it so both of them have the same power of 10. And luckily, we know how to do that because we know how to manipulate numbers. So the easier way, I'm going to say, is to change this one, to change Texas. Instead of making this a smaller number, we can just make this a bigger number. So let's change Texas to have a power of 4. 4, so it's going to be the same power as North Dakota. I need to change it bigger by 3, because if I'm making this smaller by 3, I need to change this number bigger by 3. So it's going to look like that. And notice I only moved it 3 times. So again, since I made 7 into 4, which is 3 smaller, I had to make our initial number 3 bigger. And we'll keep North Dakota the way it is. Now, let's write it out. What we can do here, and this is kind of the opposite of distribution, you're undistributing things, is we can essentially take out the powers of 10 because they're the same. So if we take it out from both of them, it doesn't actually go away. We're just going to undistribute it. It leaves behind our numbers. Now we can actually just do these numbers. So now instead of doing the whole multiplication of 26 million and 69,000, we only need to subtract 2,006. So I'm still going to cheat and use my calculator. Take a look. That's the same thing we got over there. Now we should leave this in scientific notation. So on a test, if it asks you to do this, you could do it the long way and then change this to scientific notation. So let's take a second and do that just so we can check it with our other answer. So we would have 2 as our front number with a decimal afterwards, all the other significant numbers afterwards, so the 5, the 9, the 3, the 1, times 10. And then we need to decide what that exponent is. So it goes 7, it gets smaller by 7, so this is a positive 7. So let's check if that's the same thing we get over here. This is close to scientific notation, but it's not because we need the decimal to be here. So we need to be 2.5931. So how many times do we need to move it? We need to make it smaller by 1, 2, 3. So we need to add 3 to this 4, so we get to 7 again. Oh, those are the same. For really, really big or really, really small numbers, this method is actually much easier. I know that right now, this looks easier and it's the way that we're familiar with, and if you have a calculator, it's nice. But again, if you're going to do really big or really small numbers, a calculator can't even help you there. But either way, you get the same answer. Okay? And always pay attention from now on if the answer should be in scientific notation. In which case, getting something like this or getting something like this would only get you a 3. Now, I'm actually not going to be showing you example of addition right now, but it's the exact same thing. It's just instead of subtraction, there'd be an addition there. Instead of subtraction here and subtraction here, they'd be addition. But now let me show you multiplication and division. Take a second to read this problem. The reason I chose this is because, and the reason it's so long, is because I want you to see some of the real vocabulary that scientists use and real numbers that scientists work with all the time. So the influenza virus is 130 nanometers. A nanometer is one of, what number is that? 1,000, million, billion. So 1/1,000,000th or 1 to the -9th of a meter. Remember, this is a meter. So a nanometer is 1/1,000,000th of this. So the influenza virus is 130 times 10 to a -9 meters. Let's change to true scientific notation, which is 1.3 times 10 to a -7. The reason for that is because here we have 130, so we had to move it over 2 places, making this smaller by 2. So we need to make the exponent bigger by 2. So -9 plus 2 gives us -7. A carbon atom is 340 picometers. A picometers is what is even that number? 1,000, million, billion, trillion. So 1/1 trillionth or 10 to a -12 of a meter. Remember, this is a meter. So 1/1 trillionth of this is how big a carbon atom is. Crazy, crazy small. So a carbon atom is 340 times 10 to a negative 12. Change it to scientific notation. So we need to make this number smaller by 2. So we make the exponent bigger by 2. Negative 12 plus 2 gives us a negative 10. So now here's the actual problem. How many carbon atoms can fit inside the influenza virus? So what kind of problem is this? Multiplication, division. If I'm trying to think how many things can fit inside of something else, I want to break that thing into groups of sizes, the groups that are sizes of that other thing I'm trying to fit in. And when you're breaking things into groups, that's division. So this is your division problem. And if you want to write this on there, might be a good idea. This is a very common problem that you'll see in our books of how many can fit inside something else. So whenever you see that, it's division. If you want to make a note of that, that might be a good idea. So we need to divide the influenza virus by the carbon atom. So we just need to get those numbers and just divide them up. So we're going to deal with this in scientific notation because I bet you don't want to write those numbers actually out. If you do, go ahead. You can show that to me another time and I can make fun of you for doing it the long way. So let's do this with the scientific notation. So the virus was 1.3 times 10 to a negative 7. So let's write that down. The atom, the carbon atom, was 3.4 times 10 to a negative 10. One of the nice things about starting in scientific notation is a lot of times the end result is pretty close to scientific notation, like you might need to move it 1 or 2 decimals, but it makes your job easier. Let's separate these. Right now you're looking at this, you're like, I don't even know what to do with this. So let's separate them. Because in math, you can do that. So we have 1.3 over 3.4, and then we can put the 10s over each other. Hopefully now it's looking a little bit more similar to something you've done before. This is just a regular division problem that you've done since like 3rd grade. So let's grab our trusty calculators and do 1.3 divided by 3.4. Hopefully you got the same thing I did. And let's round 2 decimal places. Since these have only two numbers, let's round to 2. So I got 0.38. Hopefully that's what you got. If you didn't, let me know. You can put it in the comments or come yell at me during class. Now, what about the tens? Well, we just did an entire half of a unit on dividing things with exponents. That's the quotient rule. When you have numbers with exponents and you're dividing them, you subtract the exponents. So you're going to do a negative 7 minus a negative 10. Minusing negatives, I know we hate those. Negative 7 minus a negative 10. When you're minusing a negative, it becomes plus, just the whole thing becomes positive. So we have a negative 7 plus 10. So if you're $7 in debt, you find $10, you now have $3 because you can pay off that debt. And that's actually our answer. It's not how we're going to leave it, it's not the form we're going to leave it, but that's actually the answer to this entire problem. So now let's change this to scientific notation. Because like I said, it's pretty close. We just need to move it 1 decimal. Now we need to make this bigger by 1. So we're going to need to make this smaller by 1. So we're going to change it to 3.8. So because we made it bigger by 1, we're going to make 3 smaller by 1. So we're going to turn it into 2. And that would be your answer. Because of course, now that we're doing a unit on scientific notation, you should be leaving your answers in scientific notation. Now, I know some of you want to know the actual number because you're looking at that, you're like, I can't quantify what that is. Let's expand it out. And you don't have to write this down, but for some of us more nerdy people, we'll like to look at it. If we expand this out, this means that this number is 2 bigger than it actually shows. So it was here, it's going to move over 1, 2 to there. So you can fit 380 carbon atoms inside of the influenza virus, which is actually good amounts considering that these both are very tiny, tiny, tiny things, way smaller than our cells.